We just defined embedded submanifolds in Euclidean spaces. What we want to define now is the notion of abstract manifold. And how are we going to do that? We're going to use the ideas of the embedded case and then generalize them to the abstract case in order to obtain a definition. Here we have a picture that you can find in Hirsch's book, Differential Topology. In the picture, we have two open subsets of, let's say, an embedded manifold, and we have two parameterizations. Of course, the arrows are not pointing in the right direction for parameterizations, they're pointing down, and for parameterizations, they should be pointing up. But the point is that here phi and phi j are considered local charts, and local charts are the inverses of parameterizations. So what we get is a situation in which the first open set is parameterized by an open subset of R to the power n, and the second open subset of our manifold is parameterized by another open subset of R to the power n. Even if these two sets have points in common, that does not imply that the domains of the parameterizations have points in common, like it happens here in the picture. These two open sets are disjoint. But we could actually try to reproduce the manifold without actually knowing these sets. How can we do this? The idea of parameterizations is that they identify sets. They identify this open subset of the manifold with this open subset of R to the power n. So if we replace this open set with this one, we're not losing anything because essentially they are the same. The parameterizations, or if you prefer local charts, are just identifications. The same thing happens if we consider U sub j. We can identify such an open set of our manifold with this open subset of R to the power n. And in this way, we have two copies of the U's. But we have a problem, obviously. If we consider now a point here, okay, there are two parameters that are sent to that point. One parameter for the first parameterization and another parameter for the second. And this is an issue because obviously we don't want to split the point into 2 points or 3 or even infinitely many. So the way of recovering the union of ui and uj is just identifying these points. And this is exactly indeed what the coordinate chain does. So we can just consider the domains of the parameterizations and identifying points by using the coordinate changes. In that way, we are going to obtain another model of our manifold. And that idea is the idea that we are going to use to define what it is an abstract manifold. Okay, here we have a definition. A manifold is always going to be a topological space X, and it's going to be even a topological manifold of dimension K. What is that? It's just a topological space that is locally homeomorphic to R to the power K. In other words, for every point there exists a neighborhood of the point that is homeomorphic to an open subset of R to the power K. In these conditions, now we already have a topological manifold. We can, or if you prefer a topological space, we can actually define what it is a CR manifold. The R over here can be a positive integer number. We are not going to consider in general 0. We're not going to consider topological manifolds because the theory for such manifold is substantially different than the properties that differentiable manifolds have. We are going to consider sometimes also R equal to infinity, and sometimes we can even consider CW manifolds, in other words, real analytic manifolds. Okay, so what is it a CR manifold? We are going, something is, X is going to be a CR manifold of dimension K if there exists an open cover of X. That makes sense. X is already a topological space, and a family of maps, indeed of homeomorphisms, Phi defined in UI and whose target is Vi, such that besides being homeomorphisms, they satisfy the following properties. Vi is an open subset of Rk for every I. So here we have just open subsets of an Euclidean space. And again, we're going to have a coordinate change because there are points that are going to be in several of these open sets, in 2 of them or 3 or even infinitely many. And so because of that, we're going to have something that it is just our map of change of parameter, which is going to be phi, the inverse of phi composed with phi j. This map is defined in something that is not an empty set if ui intersects uj. And in that case, we are going to require that this map, that because of the property that the phi's are homeomorphisms, is defined between open subsets of R to the power k, we are going to require that this map is a CR diffeomorphism. Without requiring anything, it could be a homeomorphism between open subsets of Rk. But we want to give a structure. The topological structure does not suffice for us. So we require this compatibility condition between, let's say, the structures that we are actually providing for the open sets of the cover. And this compatibility condition is just that this homeomorphism has to be a CR diffeomorphism. It has to be CR, and the inverse has to be also CR. So in this way, we obtain a definition of abstract manifold that is actually inspired by the properties and by the definition of embedded manifold. If M is a submanifold of an Euclidean space, then we can consider the local charts as the inverses of the parametrizations that we saw previously. Okay, so let's process the information that we just saw. The phi's are called local charts. Okay, these are actually the homeomorphisms between open subsets of our topological space and open subsets of an Euclidean space. The family of these local charts is called CR trivialization atlas. The R, as I said, comes from the compatibility condition between different local charts. And what we can actually use these local charts for is basically doing differential geometry. We can define, for instance, differentiable maps. For instance, if you have a map between abstract CR differentiable manifolds, we say that F is differentiable of class CS, S has to be less or equal than R, We are going to discuss that point very soon. We say that f is differentiable of class CS in a neighborhood of a point if there exist local charts. Obviously here I wrote this in this way for brevity, but the point X has to be contained in the domain of the phi I chart. Phi I is a local chart for M, and it's defined in an open neighborhood of the point X. And also we need that the image of X by the map F has to belong to the local chart, to the domain WG of the local chart psi sub j, which is a local chart for M. So in that way, we have a map that is defined between an open neighborhood of actually phi I applied to X and R to the power N. And we can actually discuss whether or not that map is of some differentiable class, because it's a map between open subsets of Euclidean spaces. And we say that f is differentiable of class CS in a neighborhood of a point X if this map over here is actually differentiable of class CS in the neighborhood of the parameter that corresponds to X, of phi I applied to X. If that happens, we say that is CS in a neighborhood of X. This expression over here is called the expression of f in the local charts phi I and psi sub j. And it's the way in which we can interpret, we can work very, very simply with maps between differentiable manifolds. We use these local charts to translate, to transfer this, to interpret actually, at least locally, these maps as maps defined in Euclidean spaces. Okay? So the definition of manifold and the fact that locally are very simple because they are essentially open subsets of an Euclidean space makes, in some sense, our life much easier, because we can translate the properties of the maps between differentiable manifolds to maps to properties of maps between Euclidean spaces, which is very nice and something that is going to be very useful. But there is always a downside. And the problem is that we have to check out that the definition we just gave does not depend on the choice of local charts. If that were the case, and for instance, this map over here could be CS for some choice of local charts, but not for some other, then that properly couldn't be intrinsically defined, and it could be useless for our purposes. So we have to check that such a thing actually happens, that the property does not depend on the choice of local charts. And that's the reason that we introduce the compatibility condition. We introduce a CR compatibility condition between different local charts. The idea is actually being able of defining intrinsic properties. I said that we're losing something because we have to check that actually the properties do not depend on the choice of local charts. But we do not lose very much because all these proofs are essentially very similar. So let's see what happens in the case at hand If we consider two other local charts, phi sub I prime, let's say, that could be a local chart defined in a neighborhood of x for m, and psi sub j prime, that could be a local chart defined in a neighborhood of f of x for n. We have to actually see whether or not this map over here is of class CS in a neighborhood of the point phi sub I prime applied to x. Okay? But the issue is that this map can be actually written down as a composition of three maps that are actually these three maps over here. The first one, or this is the first one, it's going to be a CR diffeomorphism as a consequence of our compatibility condition. And the last one is also a CR diffeomorphism. We have to check out what happens in the neighborhood of psi I prime applied to x. Okay, so this is going to be a CR diffeomorphism. The image of this point by this map is psi I applied to x, but in the neighborhood of that point, this expression is of class CS. And again, this one over here is a CR diffeomorphism. So when we compose these three things, we are going to have something that has differentiable class CS, because CR implies CS if S is less or equal than R. And that's the reason, because we have to consider S less or equal than R. Otherwise, we could have situations in which the map, the expression of the map in some local charts could be CS, but it couldn't be CS in other local charts. So in order to define intrinsic properties, we need this compatibility condition. It's absolutely necessary. A local chart, phi sub I, of a CR differentiable manifold is going to be a CR diffeomorphism. Notice that the domain of the local chart is an open subset of our manifold M, whereas V sub I is actually an open subset of an Euclidean space that has a differentiable structure. So we can ask whether or not this map is actually CR, a CR differentiable map, or even a diffeomorphism, because this map is actually a bijection, it's a homeomorphism. What do we have to do in order to know whether or not this local chart is diffeomorphism? It's just considering its expression in local charts. We have a natural local chart for M, which is going to be phi sub I, and we are going to have also a natural local chart for the open subsets of the Euclidean space, which is going to be just the identity. So the expression in those two local charts, phi sub I and the identity of our map, phi sub I is this one, and that's the identity, and the identity is a diffeomorphism. So phi sub I is going to be a diffeomorphism. It's going to be a CR diffeomorphism. So we can interpret local charts as diffeomorphisms between open subsets of our manifold and open subsets of some Euclidean space. It could be R to the power n, where n is the dimension of the manifold. Okay? As I said, this family of local charts is called CR trivialization atlas. And I repeat again, the R is actually associated to the compatibility condition. We require that the inverse of one local chart composed with another is always a CR diffeomorphism. Given a CR atlas, there exists a unique CR maximal atlas containing A. We are going to call this, for the time being, A sub M. And a CR maximal atlas is called, by definition, a CR differentiable structure. The pair consisting of the differentiable manifold together with the maximal atlas is called CR differentiable manifold. Okay? And an interesting question is, what do we need in order to say that some map belongs to the maximal atlas? Okay? For instance, imagine that we have a map phi between an open set U of our manifold M and an open subset B of R to the power small m. Small m is going to be the dimension of big M. Then we want to know whether or not phi is an element of the maximal atlas. And it is going to be such an element if and only if phi is a diffeomorphism. As we said in the previous slide, local charts are just diffeomorphisms between open subsets of our manifold and open subsets of an Euclidean space. So we need that phi is a homeomorphism, okay? And then we need to check the condition that it is a CR diffeomorphism. And in order to do that, we just need to consider the expression of phi in local charts, and it's going to be this one. Again, to the left, we don't have to compose with anything because the target space is already an Euclidean space. So what we need is that this expression over here is a CR diffeomorphism for every I. If this thing happens, then this map is going to be an element of the maximal atlas. And in that way, we see that an atlas determines a unique maximal atlas that contains such an atlas. In this lecture, we considered the definition of an abstract manifold and also of a differentiable map between two differentiable manifolds. Also, we discussed the interpretation of a local chart for a manifold as a diffeomorphism between an open set of the manifold and an open subset of an Euclidean space with the natural differential structure in Euclidean spaces. In the next lecture, we are going to introduce some examples. The first one is going to be the Cartesian product of two differentiable manifolds, for instance, of class CR. And we are going to show that such a Cartesian product is also a differentiable manifold of the same class of differentiability. Also, we are going to see an example of an abstract manifold that it is easier introduced as an abstract manifold rather than as an embedded manifold. And it's going to be the real projective space. We are going to see that it is fairly easy to give local charts for the real projective space that show that such a space is a compact manifold, indeed a real analytic compact manifold. Thank you for your attention.